The Richter energy number of an earthquake is the base 10 log of the amplitude of the quake vibrations. Now, maybe a couple weeks ago that would have sounded like blah, 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 right? But now I think we're comfortable enough to be able to translate this into English. Yeah? All right. The Richter energy number, can we call that R and you be okay with that? Okay. The Richter energy number of an earthquake is, what does that mean? Equals, good, the base 10 log of the amplitude. So that sentence in English narrows down to that sentence in algebra. Are you okay with that? Okay. The Seattle quake of April 29th, 1965 measures 7 on the Richter scale. So let's look at Seattle. The Richter energy number is 7, so where does that go? R, good. So 7 log of A. How am I going to solve that for A, for the amplitude? Oh, write it in exponential form. Right. Okay. 10 to the 7th power equals A. Now, I'm going to go ahead and leave that 10 to the 7th power because actually writing 1 with 7 zeros after it's not going to make much sense to us, is it? This is going to make more sense. Okay? What about San Francisco? The San Francisco earthquake of 1906 measured about 8.25 on the Richter scale. So 8.25 equals a log of A. How do I solve for A there? Good, same way. So 10 to the 8.25 equals A. To those who know little about logarithms, 8.25 does not sound much more severe than 7. Using what you know about logarithms, tell how many times more severe the San Francisco quake was than the Seattle one. If I know the amplitude of both of them, how do I figure out how many times one more is severe than the other one? I divide, right? Okay. So 10 to the 8.25. It's like I'm finding the ratio, right? Yes? So 10 to the 8.25 divided by 10 to the 7. What's that? Oh, yeah, we just used our calculators for that, right? Good. 10 to the 8.25 divided by 10 to the 7th. $17.78. Would that work? 17.78 what? Times more severe. So to go from a 7 to an 8.25, you knew it would be more than 10, right? Because we know this is a logarithmic scale. It increases by a factor of 10 for every number. So to go from a 7 to an 8.25 is going to be 17.78 times more severe, or almost 18 times more severe. That's a pretty big deal, isn't it? Okay? Because we're finding the ratio, we're trying to find out how many times more severe one is the other. So that ratio, that division, helps us figure out how many times more severe it is. Okay? Good question. The loudness of sound is measured in decibels. Anytime we talk about decibels, I think about football. The Seattle Seahawks in particular. Do you know why? They're very loud, right? They have the 12th man. They're like, we're the loudest stadium in football. And maybe they are, maybe they're not. I had a great picture to show you on my phone. I can't find it. I just took a picture of my television the last time we were watching Seattle because they always talk about decibels when they're there, when they're watching the game, right? Okay, but here's something that is kind of cool, and I'll show you to you in a minute, so it will make some sense in this situation. Okay, so the number of decibels is 10 times the base 10 log of the relative acoustical power of the sound waves. Again, before that might have sounded like a bunch of gobbledygook, but we're good, right? So what does it says? Decibels is what? 10 times the base 10 log of the relative acoustical power. Again, is that pretty simple? Pretty straightforward? Okay. So what? What do we do? Does it give us the decibels or does it give us the relative acoustical power? So what should we do with this? Plug it in for R. 10 log of 1. Does it make sense that the number of decibels at the threshold of audibility would be 0? Like when I can very first start to hear something. Yeah? Okay, so what about soft recorded music? Okay, so let's be careful. It says calculate to the nearest decibel. So what are we going to write? 36. Okay. What about loud recorded music? 88? Is it 88 miles per hour? No. 88 what? Decibels, right? Okay. What about a jet aircraft? $126. What about the threshold of pain? Sounds like a band or something. A great band? Yeah. Okay. So what's the decibels of a threshold of pain? 130. No. 123? Thank you. Sorry, I thought I heard 126. Is it 123 or 124? Uh-oh. My paper's a mess. Oh well. I bet the teacher will get over it. She'll be okay that I got the right answer. So here's what I have on my phone. It's a decibel level. So why in the world is it not 0? There's still noise in the room. What noise is in the room right now? There's the air conditioner. There's the projector. There's y'all. There's me. Right? When I start talking, sometimes it goes up to 70. Sometimes it's in the 60s. So I'm almost as loud recorded music. Well, that's not really fair because my mouth is what? A foot from the microphone on my phone right now? Okay, so that will make a difference. Because if you talk from the other side of the room, what's it going to be at? So it got up into the 40s, but even though it's in the 60s or something with me, right? Because I'm much closer to the microphone. Okay? I just think it's cool that even though we're in the room, even if we all stood completely silent, there's still stuff happening in the room, isn't there? I just thought that was pretty interesting. Okay? So, Richter scale is a logarithmic scale. Decibels, logarithmic scale. Something that quite a few of my students in previous class periods know is about this. Because I'm pretty sure you guys have already talked about this if you're in chemistry this year. Or if you were in chemistry last year, you talked about it, right? The pH scale, guys, that is also a logarithmic scale. Okay? These numbers up here are really what? They're really big, aren't they? What about these numbers? They're really small. Okay? So this is kind of a way to show you that this is one of the reasons why we have logarithmic scales. So that we don't have to deal with numbers really, really big or really small. We can make it into numbers that make sense to us. Okay? So, the strength of an acid solution is measured by its pH, or power of hydrogen. Okay? The pH is the negative of the common logarithm of the hydrogen ion concentration. Yes? How do I write that in English? pH equals negative log of what? Yeah, the hydrogen ion concentration, right? Okay. Well, what base is this log? Because it doesn't say. Wait, does it say base 10? Did I misread it? Oh, it says it's the common log, right? And we know that the common log is base 10. Very good. Very good. Okay, so do you know anything about pH before you start doing this math? Do you know the pH of water? What we want the pH to be? Yes, we want it to be 7, right? Then it's really, truly a neutral water, okay? So let's put in negative log of this number right here, 1 times 10 to the negative 7th. What is it? Nice. Just like we knew it should be, right? What about blood? Do we want that to be real acidic? Well, yeah, no, right? Not at all, okay? Do we want it to be real basic? Basish? I don't remember what to say. Basic? Okay. Do we want blood to be real basic? No, we want it to be what? Pretty neutral, don't we? Okay, so when we put negative log of 6.3 times 10 to the negative 8, what do we get? 7.2? Yeah? 7.2? Okay. What about hydrochloric acid? Is that an acid? Well, it should be since it's called acid, right? So do we want that number to be really low or really high? Really low, right? Okay. So negative log of 2.5 times 10 to the negative 2. 1.6. What about Grandma's lye soap suds? Do we want her to wash our clothes in acid? No. No, we don't. So what do we get? 11.03 or something like that? Yeah, okay. This is the kind of stuff that's interesting to me because this stuff is real. Scientists do this all the time. Scientists do this all the time. Scientists do this all the time. Other people besides me telling you, oh, you're going to use this every day in the real world. You know better than that, right? You know better than that. But here's some very, very specific examples about where logarithms are used outside my classroom in a really real working environment. I can't tell you that if you become a chemist that you're going to be doing logarithms every day. Because chances are the logarithm information will be built into the computer program that you're using. Okay? But at least now you know what's behind this scale, and what's behind this scale, and what's behind the Richter scale. Yes? Okay. On the back, there's a couple problems. I want you to circle, please, number 6, number 8, number 9, and number 5, because I want to throw you off by going out of order. And then I also want you, on the other worksheet I gave you, let me see if I can find my copy real quick. I want you to circle problems number 1, 2, and 3. Okay? I needed to make sure she had the problems to do before she left. Okay? I still want to do number 7. That's why I didn't circle it for you on this one. I want to do number 7 for you. Okay? You deposit $2,000 into an account that pays 7.5% interest compounded continuously. How long will it take for the balance to reach $2,400? Well, here's the deal. You've seen these formulas before. We've talked about these formulas before when we talked about exponents. And when that was true, we were solving for A and for P. Every single time we were solving for A or P. What we ended with or what we started with. We wanted to know one of those two values. Now that we're dealing with logarithms, and we know how to get variables out of the exponents, what could we solve for in these problems that we could not solve for before? The rate and what else? What else is in the exponent? Yeah, the time, right? We can solve now for the rate and the time. Okay? Now, we can still solve for A and P, right? We already have the skills to do that. But with our logarithm solving skills, we can solve for the rate or for the time. Okay? So let's look at 7. Which one of these formulas am I going to use for 7, first of all? How do you know it's compounded continuously? Yeah, it says very clearly, right? Just making sure. So A equals P e to the RT power. So what do we know from this equation that we can plug in? That we can substitute? Do we know how much we ended with? Yeah, where does that go? For A, yeah, 2400. Do we know how much we started with? 2000, where does that go? P, that's the principal, that's what we start with. E, we know is that number in our calculator, right? What's the rate? So 7.5%, so what goes in the problem? 0.075. Otherwise, it's 75%. So we got to be careful about that. If you find a bank that's given 75% interest, you better tell me because I'm taking them all my money. All of it. Okay? And then what about the T? What's the T? Oh, that's what we don't know, right? It's asking us how long. So that's what we're solving for. So what's our first step in solving for T? Yes, we have to get the E by itself first. So what do we do first? Very good. Divide by 2000. When I divide by 2000, I get 1.2 equals E to the 0.075 T. Now what? It is an exponential form, so we do want it in logarithmic form. Very good. So log base what? E of 1.2, good, equals 0.075 T. Now, we have a problem. Not really a problem. Do we write that? Do we write log base E? No. We are not stupid people, right? We're very intelligent, especially in the way of the logs. What do we write instead of log base E? Natural log. Very good. Natural log of 1.2 equals 0.075 T. Now, is it wrong that I wrote it right here? It's not, right? I was just taking this and putting it in logarithmic form. I went ahead and wrote it like this, so I made sure I have everything in the right place. But now I am going to go correct what I wrote so that I don't look like a logarithmic idiot. I mean, strange one. Because idiot is not a nice word. Shh. Okay, so how do I solve for T? Good. Divide by 0.075. Good. Divide by 0.075. So this side of the equation, I can just put that straight into my calculator, can't I? So natural log of 1.2 divided by 0.075. What do you get? Two point what? You got 2.7? I didn't get 2.7 either. That's what I got. 2.43? 2.43 what? Yeah, years. Because it's asking how long, right? And based on everything that we already know about this, we know that's talking about years. Okay? Is that a hard problem? No, why? Because we've practiced solving logs. Did you get it? You still got the wrong one? Huh? Oh, okay. I think it's because you know how to do logarithmic problems now. You feel more comfortable with it. Okay? So you have the ones I asked you to circle to do for homework. Are there any questions? Oh yeah, look at this ugly side. Why in the world did I give you 42 problems on this side? Yeah, practice, right? Practice. I didn't want to just leave it blank. I have to use this piece of paper anyway. I might as well copy some problems for you to work on for extra points, extra practice. Okay? Any questions?